All right, everyone. In this video, what we're going to go through and do is run some independent sample t-tests in Stata, and then go through and run some calculation of effect sizes in the program as well. In the previous video, we went through and did our data screening for the independent sample tests for these data. If you recall, we didn't find much in terms of, we had one case with missing values. We didn't find much in terms of distributional problems. Skew and kurtosis looked reasonable based on at least what we had. Box plots and histograms also looked reasonable. We didn't find anything in terms of extreme values. The biggest thing in these data, remember, is we've got a large discrepancy between our two groups. We've got 5 men, 5 women in this between groups analysis. Just as a refresher, what we're doing here with these tests is looking at differences in marital satisfaction and social desirability scores across men and women diagnosed with PTSD subsequent to a motor vehicle accident. So what we're going to do is compare those two groups using our independent sample t-tests. Outside of having small and unbalanced design, things looked like they were okay. But we would want to note that the one thing that we didn't do in the screening was test for homogeneity of variance. We'll do that in this video. But other than that, once we've gone through and run those, we'll go through and we'll calculate confidence intervals, calculate effect sizes, we'll conduct our hypotheses test, report S values and Bayes factor bound. Just as a refresher, effect sizes for our independent sample T, we've got a lot of different options. Our Cohen's D is just a general mean 1 minus mean 2 over the standard deviation, but remember, we've got a number of different standard deviations we can work with our independent sample test. So if we get into more specifics, we could calculate a Glass's delta. Remember that this is the difference between our two groups over the standard deviation of some baseline or control. Now here in this case, we've got men and women. I don't know if either men or women make a good baseline or control. So if we don't have a good sort of conceptual baseline or control, we might lean against Glass's delta. But what we could do is we could conduct what's often known as Hedges G. Here we're taking the difference between our two groups, and we're dividing it by a pooled standard deviation. Remember, we went through in class how to go through and calculate our pooled standard deviation. This is nice because we get to use the standard, or sort of the pooled standard deviation of both of our groups, and using that as our standardizer. Only thing that we might want to think about is in cases where we have quite small samples, we know that our effect sizes can be inflated. They're bigger than what they should be in terms of corresponding to the actual population parameter. And so we can do with our Hedges G is we can go through and introduce a correction. This is sometimes called Hedges unbiased G. And what it is just our effect size G here times 1 minus 3 over 4 times sample 1 plus sample 2 minus 2 minus 1. And what this is going to do is it's going to give us a decimal that provides a downward correction for the G that we collected here, or that we calculated here. So these are our options in terms of effect sizes. Whenever we're running these, we just want to know, be specific which effect size we're calculating and why we've gone through and chosen that. Okay. Other thing we're going to collect or calculate, remember we're calculating S values. This is going to be the natural log of your p-value over the natural log of 2, absolute value of that, and then you're going to take your S value, round it to the nearest whole integer. This is just a complementary statistic giving us a different look at strength of evidence against the null hypotheses. Again, your S value conceptualizes observing a sort of whatever that S value is, that number of successive heads in tosses of a hypothesized fair coin. If our S value is really high, we would suggest or think that that coin probably isn't a fair coin if I flip 50 heads all in a row, right? So we're going to calculate our S value here. and then we're going to calculate a Bayes factor bound. Again, remember that this is an odds ratio interpreted as the strongest case for our alternate hypotheses relative to our null based on the available data. Again, I had sent you some general interpretive benchmarks for Bayes factor bound, but again, once again, this is just calculated as 1 over negative base E times your p-value times the natural log of p, again just giving us a different look at strength of evidence against the null or for the alternative hypotheses, just to help with our interpretations. Okay, so we will close this down, go back to our data. The handout that we're going to be using here is our independent sample t-test for Stata. Again, using our MVA t-test set, we're looking primarily at gender, 1 male, 2 female, and then our outcomes are our Locke-Wallace marital satisfaction scale and our Marlowe-Crown social desirability scale. Okay, so we've gone through and screened everything except homogeneity of variance. So we want to go through and test this. So if we go to our do file, up here is all the screening that we had done, but we're going to start with our independent sample t-test. Is we're going to use this rovar command, and what this is going to do is it's going to give us our Levine's test for the Locke-Wallace and our Levine's test for Marlowe-Crown. Now here we've got rovar Locke-Wallace total by gender, so this is my grouping variable, this is my outcome. Same thing for the Marlowe-Crown. Okay, so if I go through and I run this, I see that this p-value here, this is going to be the p-value for your Levine's test, analogous to what we're seeing in SPSS. And what this is telling us here, if we go through and take a look, here's mean value for men and women. Here's the standard deviation for men and women, sample size for men and women, total, and then here's our Levine's test. And so our Levine's test here has a p-value of 0.568, so we definitely not even close to threshold, so we would fail to reject our Levine's test, and this is actually good, right? Remember, with our Levine's test, we want to fail to reject the null hypothesis, because the null hypothesis is that the variability in our two groups is equal. And so if we fail to reject, that means they're at least reasonably similar. Now the concern here is that we have a very small sample, and so this Levine's test is going to be not terribly hugely powered, but at least it looks like here things are looking relatively okay in terms of variability. So in terms of marital satisfaction, we would probably claim that we have don't have a great deal of evidence for a violation of homogeneity of variance here. Okay, but if we go through and we take a look at our Marlowe-Crown, it's quite a bit more ambiguous. Okay, so we've got our variance, standard deviation for men, standard deviation for women in terms of social desirability. Remember that this is actually a test not of standard deviations, but of variances. If I go through, take a look here, and if I go display, so this is my standard deviation. If I take that to this, if I square that, so I've got a variance for men of 46.3. For women, my variance is going to be 16, right? And so that's a reasonable size difference. Now my Levine's test doesn't meet criteria, conventional criteria for statistical significance. It's 0.054, right? So we're not less than 0.05, but my concern is that we've got a really, really small sample, so this test doesn't have a lot of power. If I actually look at my variance estimates for my men are quite a bit larger than variance estimates for my women. The small sample size complicates interpretation of this, but I don't know that I would be confident in a claim that the variability of social desirability is not different across men and women, at least based on these data, and so I want to keep that in the back of my mind. Technically, we failed to reject but this is borderline enough, and this difference into the two variances is enough that I might have some concerns about this. So we're going to keep that in the back of our mind. Okay. So again, if I were to go through and finish out my screening summary, we'd say little evidence for violations of homogeneity variance across men and women for our Lock-Wallace total, but our Levine's test is marginal, and we might say that we may have evidence for violations of homogeneity variance here. Hard to say. Okay. All right. So what we're going to do then is we're going to run our actual t-tests. And in Stata, these are pretty easy to request. We just say t-test, my outcome by my grouping variable. So here is our t-test for Lock-Wallace total, t-test for our Marlowe crown. You can run these pretty easy. Go through, run that. And here, when we're going through taking a look at differences in marital satisfaction across men and women. So for my men, I have only 5 men in my sample, 21 women. Mean for my men, 80.2. Mean for my women, 108.9. This is standard error of the mean. Here's my standard deviations. 95% confidence intervals around the means for men and women. Okay. But then what I'm going to go through here is, and this is combined. This is number of observations, means, standard deviation, standard error, standard deviation, and confidence interval for the full sample if we collapse across men and women. So this is just some descriptive stuff that we're probably not too concerned about necessarily in terms of our tests. Here's what we're going through and taking a look at. So we've got a difference of across men and women of 28.6 degrees, with women reporting higher levels of marital satisfaction than men. Here's the standard error for this difference. And so what I end up with is a 95% confidence interval for the difference in marital satisfaction across in the population of men and women, ranging from estimates of negative 54, a difference of 54 points lower in men, to an upper limit of only 2.5 points different in men. Okay, so my best guess for the difference in marital satisfaction on the Lock-Wallace across men and women is 28.6. But based on the data that I've got, anything from a difference of 2.5 points less for men to 54, close to 55 points less for men is going to be reasonable based on the data that I've collected. That's a really, really, really wide confidence interval. So really what we're seeing is anything to a whole lot of a difference to something that's probably quite a bit of trivial difference, right? Now, I don't know if 2.5 points on the Lock-Wallace is a meaningful difference. I suspect it's probably not. And so we've got some ambiguity in terms of, based on our confidence interval and our reasonable estimates for population differences across these two groups. I don't know, it could be anything from a huge difference to something that's quite trivial, right? So we've got some ambiguity in terms of our data. Now, if I go down through and I take a look at my actual statistical test, my test is negative 2.26 with 24 degrees of freedom. And for my two-tailed test, this gives me a p-value of 0.033. Okay. Now, traditionally, under our just hard-cut dichotomous decision, we would say that we've have enough evidence, we've rejected the null, and we've claimed statistical significance. We would say claim a difference in men and women. The problem is if we look at our confidence interval, considering quite a bit more ambiguity in terms of this. Okay, so what I can do to help sort of flesh this out a little bit is I can go through and I can run some effect sizes. Now, if we were doing this in SPSS, we'd have to run some of these out by hand or use our Excel calculator that we'll build eventually. One of the really nice things about Stata is that Stata will run all this stuff for you. Okay, so what I can do if I want effect sizes for my independent sample t-test for my Lock-Wallace, I can type in e-size to sample, Lock-Wallace total by gender, and then this is just requesting all of the effect sizes or pairwise effects that Stata will run. So if I go through and I run this, it's pretty slick. What it does is it gives me an effect size for Cohen's D. Now what Stata is reporting as Cohen's D is actually Hedges G. Okay, so this first column here going to be Cohen's or is Hedges G. This second one that's actually called Hedges G, this is Hedges unbiased G. Okay, and this makes some sense if we think about. Remember, Hedges G is just our difference between our two samples over the pooled variance, and our unbiased G includes a correction for small samples. If I go through and take a look at my point estimate for my effect size for Hedges G, and then I can take a look at unbiased G, we see that this one is smaller than this one. Okay, we've also got Glasses Delta 1, so this is going to be our delta, Glasses Delta using standard deviation for men as our standardizer. Glasses Delta 2, this is what the effect size would be if we used women as the women's standard deviation as the standardizer, and then a point bar serial. This is just a correlation. You don't have to worry about this. This is the correlation between gender and marital satisfaction. We'll worry about that in 5300. So, but what's nice is Stata is going through and it's giving you Hedges G, Hedges unbiased G, and both your delta Glasses delta values, and then it's calculating for you automatically confidence intervals around these effect sizes. We're going to do this in the next lecture, and again, if we're using different programs, particularly SPSS won't do this. There's a lot of extra things that you have to go through. What's nice is that Stata is just providing this for you automatically using this e-size 2 sample thing. So for the purposes of these analyses, I see that I've got a p-value less than 0.05. So I'm rejecting the null hypothesis of equal population means. But my confidence interval is really huge. My confidence interval is saying anything from a 2.5 point difference across men and women to anything as large as about a 55 point difference is reasonable or consistent with the data that I've collected. So that's a lot of uncertainty. However, if I go down through and I take a look at my effect size, point estimate of my effect size, if we're going through, and again, we've got really, really small samples here, so I'm going to look at unbiased G as my estimator of effect. I'm still seeing a very large effect size. So we've got an effect size of negative 0.109. That's exceeding benchmarks for a large effect. Basically what it's saying is we're seeing about a standard deviation that the difference between men and women in marital satisfaction, men are scoring about a standard deviation below women in terms of marital satisfaction. That's pretty big. Now the confidence interval on my effect size is anywhere from 2 standard deviations below to less than 1/10 of a standard deviation below. So again, a great deal of uncertainty here. So we're kind of in a tough place. Basically, we're saying the difference is, even though we've failed or rejected the null hypotheses, we've got p-value less than 0.05. Our actual difference could be anything from something negligently small to something really, really large. Okay, but our best guess is about a standard deviation below the mean, or excuse me, a standard deviation difference with men scoring, reporting less marital satisfaction than women. Okay. Last thing we could do is we can calculate S values and base factor bounds, right? And so if we go through and again pull up we could do this by hand because we've got P values here, but for the purposes of this, I'll just use my calculator. So if I go through and I take my T value, plug that in, and I've got 24 degrees of freedom. 24 degrees of, oops, yeah, I guess it's not liking the negative. Fine. Okay. So my test statistic, 24 degrees of freedom. And so this is giving me an S value of 4.9, which we would say 5, right? So basically what this is saying is that the data that we have available to us is a similar strength of evidence against the null as if we were to get 5 consecutive heads a coin that our friend hands to us says, hey, this is a fair coin. So I flip it 5 times, I get 5 heads in a row. Do I think that coin is fair? I might start to have some concerns about whether or not that coin is fair, but getting 5 heads in a row, it's not likely, but it could happen, right? And so we would say strength of the evidence against the null hypotheses here is fairly, it's not overly strong. Our Bayes factor bound is 3.24. Again, this is the data-based odds of our alternative being true relative to the null, at most about just a little over 3 times. So again, we're starting to see here that even though we have a statistically significant effect, even though we have a very large effect size, we have some questions about. So we would need to be cautious in terms of how strongly we would make a conclusion for this being something that we're confident is going to go through and replicate. Okay, so again, calculated our confidence intervals, calculated our statistical test, calculated our effect size, and then calculated our S value and our Bayes factor bound here. Okay. So this is just for our Locke-Wallace, but I guess we have at least some evidence consistent with our hypotheses that men may score lower in terms of the population of men, population of male survivors of motor vehicle accidents with PTSD may score lower in marital satisfaction than women. But then we also wanted to take a look at our Marlowe crown, right? And so remember, when we looked at our homogeneity of variance test for the Marlowe crown, it looked like we had some potential differences. We technically haven't violated or reject the null here, so we don't have, our test isn't significant, but we want to be careful. Now, if I go through and I run my t-test for Marlowe crown by gender, and I go through and run that, again, descriptives for men, descriptives for women, confidence intervals for average social desirability for score for men, confidence interval for average social desirability score for women. This is for our full set, but down here is what we're interested in within our test. So we've got a difference of about 1/4 of a point, our standard error, and then our confidence interval for these data run from 5 point lower for men to 4 point higher, 4.5 points higher for men. So we've got a huge range covering positive and negative effects. So a lot of ambiguity here. My test statistic, negative 0.11. My p-value here, 0.9127. We very clearly have failed to reject the null hypotheses here. And so we're not saying that there isn't a difference. We're just saying that these data are inconclusive in terms of determining whether or not there's a reliable difference in social desirability across men and across women. Okay. If we were to go through and calculate our effect sizes for the Marlowe crown by gender, again, we see incredibly small effect sizes, less than 1/10 of a standard deviation difference, right? So it doesn't look like there's anything going on here. There's sort of clear ambiguity in terms of sort of differences. Again, we're not saying that there's no difference. We're just saying that these data don't provide sufficient evidence to make a strong conclusion about differences in social desirability across men and women. The data that we've got here suggests, consistent with our hypotheses, the social desirability looks to be relatively similar across men and male and female survivors. Okay. Now, the other thing we could do, again, remember, because with our homogeneity of variance test, it's sort of marginal, right? We're right here. It looks like it might be, we might have a violation. So we might want to go through and ask ourselves, well, what happens if we assume unequal variances across Marlowe crown or social desirability scores across men and women? We can easily test this in Stata. In SPSS, this is equivalent to your row of tests that say equal variance not assumed. Here in Stata, we'll just request the same t-test. We'll just specify unequal here at the end, and this is just telling Stata, tell us run our test and not without assuming equal variances. And so if we go through and we run that, Again, we can say, so we've got our t-test, Marlowe-Crown by gender, unequal, and Stata is telling us we're running a two-sample t-test with unequal variances. Okay, so again, descriptives for men, descriptives for women, descriptives for the full sample. Here again is our difference, but with our corrected Satterthwaite degrees of freedom, t-value is still very, very small, still nowhere near anything that we would feel confident claiming differences. Everything is looking fairly similar. So even when we run this test with unequal variances or not assuming equal variances, basically we're saying that we're agreeing that yes, we have violated homogeneity of variance assumption. Overall impact is basically we're getting the same thing functionally that we found up here. We're just saying that with our unequal variances assumed difference here, that we're just running our normal degrees of freedom. Here we've got an adjusted degree of freedom test here. Okay, so that finishes up all of our independent sample t-test stuff. If we wanted to take a look at this in terms of our write-up, again, this is just from your lecture slides. We're going to go through here. We're talking, here in this bullet, we're talking about our what we found in terms of our screening. Here, going through a nice in-depth discussion of what we found. Here, we say evaluation Marlowe-Crown scores failed to provide strong evidence for differences in social desirability responding across male and female survivors. We're giving our difference and our confidence intervals here, saying independent sample t-test identifies observed data as generally compatible with near null differences, given our assumptions of the underlying model. Say results do, however, indicate potential for greater marital satisfaction in female survivors, with point estimate of unbiased G suggesting full standard deviation increase in scores among women as compared to men. Right. So here's our hedges G. Confidence bounds, however, identify values ranging from 2.45 to 54.84, plausible estimates for the true difference. Also worth noting that lower bound estimates supported by these data are likely not consistent with meaningful differences, given that observed variability in Lock-Wallace scores. Right. So again, variability is quite large. A 2-point difference isn't going to be all that much. Our independent sample t-test also provides only modest evidence for absolute difference, right? And then here we're talking about our Bayes factor. Bayes factor bound for these data suggests the likelihood of an alternate hypothesis is at most 3.3 times that of no difference in marital satisfaction across male and female survivors. Odds correspond to a 23.6% chance of the null hypothesis being true under optimal circumstances, assuming prior probabilities of the null and the alternate are equally likely. Okay. We also have a small and unbalanced sample. That complicates things. So what I would do is I would conclude that although the data suggests possibility of greater marital satisfaction among females compared to male survivors, strong conclusions regarding magnitude and generalizability require additional study. So again, that Bayes factor bound was 3.3. So this is saying at most it's just tipping into sort of outside of weak stuff. So at this level, we're still pretty marginal on what we found. Again, if we wanted to be something that looks maybe more appropriate for what might be written up in a journal, here's a kind of a cut down write-up of what that might look like. So again, I think this is a nice example for, even though we did for our Marlowe-Crown finding evidence of what would be meeting criteria for statistical significance by conventional benchmarks, and even finding a large effect size even when we've corrected, wanting to be careful about strength of evidence for our conclusions just based on some of the width of our confidence interval here, and some of the limited additional evidence based on our S values and our Bayes factor bound. Okay, so that works through that. Hopefully this is helpful, and if there are any questions, please let me know. Happy to help you get this stuff sorted out. So, all right, thanks.